All right, we are in 2.6 here. And we're going to go to something called the library of functions here. If you think back to algebra, there is a good amount of functions you've seen before. We're going to go through those. We're not going to sort of add any new stuff except for maybe 2 new functions just to take a look at. These are the unique ones you really don't find in algebra. And then we're going to jump to how about putting them together? Like, what? What do you mean putting functions together? Yeah, we can put them together because sometimes you need one function for a certain amount of time and then you need another function for another time. So let's go for it. So first is the linear function. And this is the way the book does it. I think I drew it for you as well already on your slides here. The linear function, of course, you think you've seen that formula before as well. Then you may have called this a horizontal line before, but this is called the constant function, which means this guy does not change. Still is exactly the same. All right. And then we have something called an identity function, a very specific linear function. We're going to use this and see this a lot later on here, but it's the one that has a slope of 1 and it goes directly through the origin. It's a very specific line. If you were to say what line is this, you would maybe just label it as y is equal to x. I think you'll see that later on like that in the textbook here, y equals x, or the fact that the y and the x numbers are exactly the same. Okay, with this we know that whenever you have a linear function you have a slope as well, and so with it here, bless you, and right, so this guy just means that this is a positive slope, because whenever we look at lines we always read them from left to right. And if it's going up, it's positive. And if it's going down, we say it's negative. And there's your constant function there. And we find out, hey, this guy just has a slope of 0. There it is. All right, and then the identity function itself. Again, this one has a slope of 1 as defined already. Good, so of course, what we'll have to do is just review a little bit of algebra before we get anywhere else. And so writing a linear function, how do we do that? Well, if you think back to algebra here, if you have g of 1 is equal to 4 and g of negative 3 is equal to negative 2, what you really have is you have these points, right? This is your input, this is your output. So over here, input and output really just becomes an x and y pair. Again, input, output just becomes an input and output pair. So we can use our slope formula for that. And which formula do we use? We use the point slope form, right? In order to go from a graph back to equation, this is the formula we use. And again, I already gave it to you here on the worksheets as a just sort of see what you get here. You get your slope. Once you calculate your slope, then you plug in any one of those points. You could use the 1, 4 or the negative 3, negative 2, whichever way you like it. But eventually, we solve it for the graph, because that's what we have here. And then what we do is we say, well, this is the linear function g of x. That's what we want to do. And where does g come from? G comes from the previous slide saying it was g of 1 and then g of negative 3. All right, anyways, for us, can you write for me a linear function of g, for which g of negative 2 is equal to 2 and g of 1 is equal to 8? Well, if you want to, you can make these into x and y pairs as well, right? Input of negative 2 gives you output of positive 2. Input of 1 gives you an output of 8. And again, x1, y1, x2, y2. And we go to our slope formula. 8 minus 2 on top. That's the subtraction of the y values. And then how about a 1 minus a -2 on the bottom. All right, let's see, that's plus plus, and how about a 6/3 looks like, and then how about just a good old 2? This should be something you remember from algebra here. All right, and the formula that we want to use, y minus y1 is equal to m x minus x1, and let's plug it in, whichever you want to plug in. I prefer plugging in 1/8, just because I don't have to deal with the negatives there initially. So how about 1 minus 8 is equal to 2. That's my slope, and it's x minus 1. Cool, I'll work with that. And simplify it so it solves for y. Distribute the 2. After that, we can subtract the 8 from both sides. Oh, sorry, no, add 8 to both sides, right? Adding 8 to both sides gets you a +6, and then we declare this to be a function, not just a graph. But we say this is the function of g of x, and that is 2x plus 6. Yeah, question.
The same answer if you use the other one?
Oh, awesome. I was waiting for that question. Okay. So if we used -2, +2, we'd get the same answer. Let's try it, because I love trying stuff. Let's make some space here, maybe like right here. And so we're going to go with y minus 2 is equal to 2 as our slope, and it's going to be x minus a -2, right? Because you're plugging in a -2 into here, so how about a little +2 right here? I love questions, they're cool. Makes you sort of think. All right, distributing the 2 out here, so 2 times x, 2 times 2 makes a 4. And then we're going to add 2 to both sides, right? And as you add 2 to both sides, gets you exactly what we have. This is so awesome. You know, and then the real fun question is why, Mr. H? Why? It's because if you think of these guys as graphs, -2, +2 is somewhere over here. 1/8 is like somewhere over here. So notice it doesn't matter which point you choose because both points are on the line anyways, right? So it doesn't matter. In fact, we could have chosen any other point. As long as that point was on the line, then we could have, and we would have got the same answer. Cool. All right, next example here. Kind of fun little thing. It's really just about the fact that we use functions everywhere. Archaeology, I don't know, looking at shark teeth. I don't know, maybe the guy likes Shark Week, I don't know. So the largest known megatooth specimen is a tooth that has a total weight of of 15.6 centimeters. So we have a length of a shark based upon the height of a tooth phenomena. That's kind of cool. So what's so fun about sharks and teeth? Well, we only have 2 sets of teeth, right? Baby teeth and adult teeth, right? And sharks, they shed their teeth constantly. Could you imagine always shedding your teeth, always going through? No way. Once was like totally enough, right? Anybody pulling their teeth with like a... Never mind, I'm going to. Okay, so what is the formula? Formula is right here. And again, just practicing plugging stuff in, really sort of basic algebra stuff, but just getting us to know that we use formulas a whole bunch. Linear formulas, quadratic formulas, any kind. This particular one is just a linear formula. Okay, so calculate the length of a shark if the length on the tooth was 16.4 centimeters. Let's see. What should we say? This is 30. Yeah. So according to the formula, the length of the shark, I'll just put S for shark. You can put L if you like, but it's going to be 0.96. I'll plug it in 16.4 minus 0.22. I want to use a little calculator for this one, if anything here. So multiply and then subtract. And anybody got an answer yet?
15.524.
15.52. I'll go with 5.2. We're good. If you're off just by a little bit back of the book, as far as rounding goes, I'm not too crazy about that. We're good if you're just a little bit off. All right, meters. Every meter is about 30. It's about 39 inches, but really this is quick comparison here. So it's almost a yard, really, in a sense, right? This is about 15 yards, so 45 feet long shark. That's pretty large. Okay, so before we get into all the library of functions that we have and just kind of quickly go through them, let's just go through just graphing a function first, seeing how it works, seeing how it looks. How do we get to the point of graphing it? It is because we make ordered pairs of inputs and outputs, and then we go from there. You can just leave it just like that. Yeah, 15.5 meters, 15.52, that's fine. Any one of those close enough would work. Okay, let's go for it here though. So remember in algebra, we were taught that if you do not know what a graph looks like, you can always make a table. And that's just kind of, again, familiarizing yourself with it here. If you're just absolutely stuck, I have no clue what this looks like. This one is actually called an extended table. You know how usually we do tables like this, right? We just have an X and a Y and we go down like this. That's a simplified table. This one is an extended table or expanded table or a work table, which means you use this number, you plug in, show the work inside the table itself, and then give yourself the pair on the outside. We know what a square root function looks like. If you make a table, this would work, right? Square root functions. In pre-calculus and calculus, almost all the time, you're going to work with real numbers. So you're not going to work with the I value. In some applications of calculus, it comes up, but almost all the time we work in real numbers. You go into electrical engineering, then you're going to work with I quite a bit. All right, so after this, we make ourselves a little table and we go like this. So voila, there's your square root function. Square root function starts at 0, 0. It sort of curves upward, and then it starts flattening out slowly, but never ever to flatten out completely. So this will keep on going and going higher. Our job is to make this little graph here. All right, if you need to make an extended table, that's fine. If you can just go with the regular old quick table, that's fine too. I'm going to do the quick table unless anybody has objections to it. Good. Nobody. So first and foremost, I'm going to do it the silly way first. Is that okay? Okay, fine. I'll do the work. There it is, and then if you do this, then you might as well do this. X and Y pairs at the end. So if I plug in a 0 into here, we have the square root of a -0, obviously, which is 0. So 0 is the pair. And it wouldn't take you too long, because you guys are sophisticated Math 15 students, that if you were to plug in a positive value, this will turn out to be, yep, let's see, not a real, we can say solution, we can say root, whatever you like. Since we're solving for answers here, I'll say not a real solution. So that did not work very well. If we go the other way here, -1, and particularly for square roots, you learn kind of quickly here, you know what? I'm not going to plug in all the values because the square root of 2 is not going to help me any. But if I were to plug in a -4, that would help me tremendously. In fact, why show all the work if I know exactly what's going to happen? I've thought about it enough. I think I'm going to give myself a -4 too. If I think about it a little bit more, how about this? When I plug it in, eventually it's going to become a square root of 9 only, is that right? Which becomes 3. And how about a -9 comma 3? And once they have this, how about you guys make the graph on the other slide? All right, and of course the honesty question. How many looked at 2.6 prior to coming to class today?
On homework or on this?
Homework or lecture or just book and just scanning it and that's it?
Homework.
Homework, okay. 1, 2. Two people passing the class for sure. The rest I don't know about. All right, hopefully you guys are on the graph already here. I would not survive college if I did not read ahead, especially in the tough classes. It's kind of certain classes you know that you don't have to read ahead. You just need to read like right before the test. History for me was like that. Like, really? Okay, why? Math, physics, no way. Read and know it before. All right, come to the graph here. So I'm just putting in points here. I know I had 0, 0. What else did I have? I had a -1, +1. Then I had a -4, +2. I had a -9, +3. So it looks like it's kind of weird. It goes like this now. There it is. Okay, make the arrow. Make sure you put a little arrow in here because it's going to keep on going. All right, the other thing you need to do for me is give me domain and give me range. And give it to me in terms of interval notation. That's the normal way we like to see domain and range. So domain and range in terms of interval notation. All right, bless you. All right, I'm going to go for it as well here. So domain for this particular function is all the x values that make a graph. So notice if I go to the positive x's here, there's no graph there. It only works in the negative range. So nothing here at all. And then whenever you're looking at domain, you're just looking at the x-axis. So what numbers along the x-axis will produce a graph somewhere here, right? And it looks like it's going to keep on going forever. Is that right? And so in this case, how about -infinity? And when I get to 0, I have to stop, but I am including my 0 because that's 0, 0 there. All right, as far as range goes, now that all's along the y-axis now. So nothing here as we climb the ladder. Looks like it starts here. And then I can always have a graph, and as I said before, this one will keep on going forever higher, just very, very slowly as we get further and further up. And so in this case, I think we go like this. We say we start off at 0 this time, and we do go off to +infinity. Okay, so that's the square root function. We looked at 2 of those kind. Let's see if we just change just a little bit. Let's see what happens here. So domain is really fixed here, range really fixed here in light of the fact that you can't take square roots of negative numbers. So what happens if there's a cube root on our hands? Oh, a cube root does and will handle negatives as well. because 3 negatives multiplied together will still give you a negative, and 3 positives multiplied together will still give you a positive. So there's the table there. Again, using the extended table. Plotting those on a little graph, and then graphing those guys will produce a little graph that looks like this. That's cool. And again, so that's the example problem. All right, f of x is equal to the cube root of a negative x. Again, graph it. I'm going to probably make a table first, but eventually graph it. And then after that, give me domain and range. And here, you want to put in numbers that you know are going to give you good answers here. So I'm thinking, well, for sure, I know if I plug in a 0 into here, right? The square cube root of 0 is still going to be 0. And then I'm thinking to myself, you know, probably a negative 8. Would that work as far as negative numbers go? Plug in a negative 8 into that. Negative of negative 8 is a positive 8. Cube root of 8 is a 2. And then negative 1 is going to work well. Plug in a negative 1, makes it a positive 1. Cube root of a positive 1 is 1. And then, of course, the opposite of those numbers themselves. Positive 1 goes in, becomes a negative 1, and cube root of a negative 1 is a negative 1. And then how about an 8? 8 plugged in as a negative 8. Cube root of a negative 8 is a negative 2. So there's my numbers. Question.
Isn't it supposed to be the one supposed to be negative 1, negative 1?
This one here?
Yeah.
Yeah, let's go for it. Let's plug it in here. So if we plug in a negative 1 into here, it's because this little negative already sitting here. That's what it is.
Oh.
So when you plug it in, you have this situation happening inside. And so now we have a cube root of a positive 1 eventually becomes positive 1. So it changes the sign inside. Okay, I think most people got the table there. And for the graph, if you haven't done so already, go for it. Plug it in those values here. See if you stay ahead of me here. I got 0, 0. Negative 1, 1. Whoa, negative 8, 2. That's all up here. Positive 1, negative 1 this time. Positive 8, negative 2. So this one, let's see how this works out. Draw it slowly here so I don't mess up too much. All right, in this case, we actually have arrows both ways, right? This way kind of curves down like this. Turns around then. And we should have something like this. Now we have arrows going both direction. So again, domain and range. If you have
Would it just be infinite in both directions for range and domain?
just how you write it here. It's going to be negative infinity to positive infinity, right? Because you always write as an interval, low number first, going up to high number. And then for the range, again, the same thing's going to happen, even though it looks like it may sort of flatten out, but it doesn't flatten out completely. It still keeps on going higher and lower as you go to the left and to the right. Okay, so those are just kind of quick little examples, really taken from algebra, the fact that we can always plug into table. That's really about it. Well, the new piece, kind of sort of new piece here that I don't think you've seen in algebra, is this whole concept of piecewise functions here. So we sometimes have to do is we break up functions. For a certain time we use one function, and some other times we use another function, just based upon what we need here. Maybe the best example probably would be like cell phones. Cell phones would be a good example, because whether you're like on a data plan or a calling plan, right? Let's say for the first 1,000 minutes, let's do a voice plan here, right? You have something that looks like this, right? You're going to pay a flat fee, right? If you use 200 minutes, never use the phone ever, you're going to pay $60. Right? And then usually they have unlimited minutes, huh? Let's change that. Let's go like this. Instead of that, let's go data plans, right? There it is. 10 gigabytes. There you go. P5. Happy now? All right. All right. Once you reach that marker, you're in trouble, right? Because then what happens is it goes like this, right? Seems like it's a very uphill climb, very fast. And so there it is. So one function operates until you have a certain data limit, and then afterwards another function takes over. Where else is it seen? Tax is a good example, right? You have certain brackets, and the general tax brackets, really, first of all. And then if you ever done taxes, you will have a blast if you ever do them. You look at these for your taxes, overall tax, it's like these miniature blocks. If you make from this much to this much, and it usually goes like $500 difference, then it goes down to a $300 difference, then $50 difference. But each of those technically is a different function. So, all right, so let's take a look at an example first before we get into this right here. And so this is a piecewise function. First and foremost, this is what they usually look like right here. You have a function, and then it equals to, and then there's sometimes 2, sometimes 3, sometimes 4, 5 tax tables over 1,000. And then what you always have to do is you have to define when it works. So we use this function if x is less than 1, like that. So just like we use, if we're going to use the constant function for our cell phone bill, if data is less than or equal to 10 gigabytes, right? After that, then we use a different function. All right, we use a different function here if x is equal to 1 or greater than 1. And so just a quick little thing, if you say f of 0, obviously we're going to use the top function right here, right? Then if we say what's f of 2, well, we're going to start using the bottom function. All right, so let's work these out just real quickly here. Not the example. Let's go to our practice problem itself. So our function, just a little more simpler. F of x is equal to x squared if x is less than or equal to -1, and then 2x if x is greater than -1. All right, the only thing that you got to be careful for is making sure that your domain doesn't overlap, which means you're going to use both functions at the same time. So one of them usually is like less than or equal to, the other one's greater, or less than, the other one's going to be greater than or equal to. And so if you have not done so already, so plug it in a -2, we're going to have to use the top function. And so we're going to be using the squaring function. At this point, the answer is 4. For a +3. Now we're using the bottom function because our number is greater than -5 this time. So now we're going to use the doubling function. 2 times whatever we put in, and the answer should be 6. All right, good. Hey, all right, example problem to give us to the practice problem here because they span the same thing here. That's right. Another one is this whole concept of speed limits. So in Peach County, Georgia, section of the interstate highway has a speed limit of 55 miles per hour. If you're caught speeding between 56 and 74 miles per hour, your fine is $50 plus $3 every mile over 55. All right, the only thing is...
That's cheap.
Yeah. You know, the only thing I don't like the word between here, because in mathematics, between actually does not include the endpoints. And that's only my little beef with this problem here. For 75 miles or higher, your fine is $150 plus 5 miles every mile over 75. So let's see how we write a piecewise function. So it looks like there's two different ones, right? One is if you're inside a certain range. One is if you're above the 75. All right, what does it look like? There it is, and notice this little extra little piece right here. So you got the $50 right away, right? Plus 3 miles, and it's again any mile over 55 miles an hour. And so because you have to subtract that out to give us that. Okay, and notice right here, here's where we have a little thing. So again, in this problem, so the between part is here. It should have been if you are traveling 56 miles to or up to 75 or something like that. So let's see, less than 75, and again, not specific here, but that's okay. And then if it says if you are traveling for 75 miles or higher, so here's your domain restriction here. Again, 150 miles right away, $150 right away, 5 miles for each mile you go over. And then it says, what's the fine if you're driving 60 miles? Notice we're using the top equation here. For 90 miles an hour, and now we're going to use the bottom equation to figure that one out. All right, practice problem number 6, our problem. Here it is. So repeat the example. If your fine is $50 plus $4 for every mile over 55 miles per hour and less than 75 miles, and $200. Ooh, things getting expensive here. They caught up with inflation, I guess. Plus 5 miles for every mile over 75. And I'm not sure if it's the same in other states. You guys from other states can tell me. But in California law, usually if it's over 85, then it's called reckless driving, and it's your car is impounded for at least 3 days. But sometimes if the officer's not very nice,
No, I
he'll
was going
30
80.
days.
No, I got caught going 87 and I didn't get it.
Whew. Okay. Okay, give you guys a little bit of time looking at that problem, trying it yourself. Maybe half a minute or so. All right, so here we go, in keeping with the way they had it written before. Okay, in this case, capital F, lowercase f, you kind of get to define that here. I'll use the same one that they used. And so now here it is. So the first one is $50 plus $4 for any mile over 55. And the way they had written is 56 less than or equal to x less than 75. I like the wording here on this problem though. It says and less than 75, so that's a little bit better wording. All right, and anything 75 or over is 200 plus any $5 for every mile over 75. And again, domain restriction for this one, x greater than or equal to 75. All right, it's part A. Part B then is you figure out the fine for traveling 60 miles an hour. then traveling 90 miles an hour. All right, for traveling 60 miles an hour, we're going to use the top function again here. And it's going to be 60 minus 55 as we plug it in, which should give us 50 plus 4 times 5. And how about eventually, I think a $70 fine, is that right?
So do you just use whichever one you want to use, or you got to use the top one for a certain number at the bottom?
Good question here. The question is, which function do I get to choose to use? And all based upon the number that you're plugging in. And that is all based upon this whole piece right here. So if the number 60 is a number between 56 and 75. If I'm going to do 90, then I have to go over here because 90 is the one that's going to fit above the 75. So for 90, it's $200 straight, and then it's anything over 75. It's going to be 15, I believe. And how about 75 on top of that? And 275 dollars gone. Just gotta say if it's worth it, that's all, right? Very okay, well, I could have. California is much more expensive than that. Yes, if you're traveling 90, imagine it's going to be a lot more expensive than that. And I kind of wonder if California uses a algorithm too, or does every county does?
They it's like $150 for a ticket, and then every mile you're going faster is $20.
Oh, cool. Okay.
Yeah.
Cool. Oof. 6,000 miles. That's 6,000. All right. So we use how we plug them in. Now let's go to graphing these guys. How do we graph them here? So it is, I have a function that says negative 2x plus 1 if x is less than 1, 3x plus 1 if x is greater than or equal to 1. Again, this is the example problem from the textbook here, but I want us to do it just to get us comfortable with it here. And then on top of that, I do want to go domain and range for these as well, just for us to get used to that as well. All right, so what do? Well, we got to focus on the number that gives us the transition, or we'll call it a transition point. It is that little 1 there. There's going to be a complete break how we view this. But notice also the two functions that we have are actually linear functions. Is that right? That kind of helps. We're going to use y equals mx plus b. So don't forget this little guy right here. But we're going to use it inside the domain restrictions that we have. So that function there, we're going to use it again for this one, understanding which in what domain restriction we have it. Okay, so let's do the top one here. So first of all, everything changes at 1, right? So really, if we use y equals mx plus b, remember we like to use that little b part, because that tells you right away where's that number along the x-axis, right? And so for the first one, since x is less than 1, 0 is less than 1, I can actually put those numbers down. We're good? So let's go for it. Except when I get to 1, I can't use that function. How does that work? Let's go for it. So my graph, here it is, negative 2x plus 1. So what I'm going to do, I'm going to put in a closed dot at 1. Everybody good there so far? And I have a slope of negative 2, is that right? So I'm just using the top function. Here it is. This is what I'm doing here. Just the top function. Start off with 1. My slope is -2/1. I'm going to go down 2. So 1, 2. I'm going to go across to the 1. I need to put it over here, except my only problem is this is my transition number. So my question is, am I using this function here? Or am I using the other function here? Using the other one, right? So I can't put a closed dot, but I can actually use an open dot because that's where the number ends. We good? So that means, let's draw it out now. So that means up until this point here, up until that 1, or x equals 1, this was the function. Okay, now let's use the bottom function here. So from here on out, I can use the bottom function here. My only problem is I still want to use y equals mx plus b. It's a linear function here. So how am I going to do this here? Well, I'm going to just eyeball it. That's what I'm going to do. I'm going to say if this is 1, technically the dot should have been right here as well, right? Can't use that dot because that's not where I'm graphing. That's not where my number is. But I'm going to go 3 up from there. 1, 2, 3. Go over 1. And that's where my graph starts. Good. So that's when I can put my closed dot. So let's put a closed dot right there. And that will be our first point. We're good? From here on out, let's use slope again, right? Because slope doesn't always just go away from the y-axis, right? If you know any point and the slope, you can graph it. So let's go for it here. So putting a closed dot there. Going up 1, 2, 3 over 1. Putting closed dot there. I think I'm good. All right, arrows to keep on going. And there is my function right there. There's my doesn't look at all anything like our cell phone function, right? But it's more abstract. Okay, give me domain and give me range. All right, for domain, the question is this. Is there ever a time, if I give you an x value, that you'll say undefined for the y values? Is there ever a time if I say an x value that you can tell me undefined or does not exist? So if I say -1, can you still give me a value for y? How about if I say 0? Can you guys still give me a value? Okay, how about if I say +1? Can you still give me a value? Yeah, we're going to actually say 4 this time, right? Because you jump to the next function. So for domain, guess what? Everything works, right? Even though there's a gap in my graph, there is no gap along the x-axis for this function. Okay, now for range, we're going to use our little ladder, right? We're just climbing up the y-axis. We're going to see the low point on this graph and the high point. So nothing here, nothing here. Looks like the lowest point is actually right here. Is that right? From here on out, I have graphs all the time, right? All the time here. In fact, 2 graphs. That's fine. That's going to go on forever, right? So really, it's the low point here, and it goes on forever. So that's what I capture here. So low point here goes on forever. So I'm thinking parentheses -1 because I'm not technically including the -1, right? If it was a closed dot on that bottom over there, then we would have included a -1. So that means it could become -0.9, -0.99999, right? But there's never a time this graph will ever reach -1. And I'm going crazy here. So let me do it correctly here. Yeah, I'm right. P5 got me all scared here. Okay, -1. And let me go to infinity. Let me take a question here. So questions.
I missed why it's -1.
Let's see. You miss why it's -1 and not +1?
Yeah.
I got it. Okay. So +1 is our transition right here. +1 is where the break in our graph, you start using one graph and you start using but that's talking about the x values. Good. For the range, you're talking about y values. You're talking about just what's the lowest point in this graph. And the lowest point of this graph is at, can't say -1, but anything above -1. So just going to say you're looking at different variables. I'm going to let you ponder that. But if you still have that question in the class, please come and ask me, and we'll try to see what's going on there. All right. This is the way the book defines it. And if you want to read through that piece there, go for it. No problem by me. Here's the way they do the graphs. They do the graphs separately. Again, we still get the same exact graph either way. All right, this is your practice one now. So all yours here. Can you graph for me the piecewise function of f of x equal to -3x if x is less than or equal to 1, 2x if it's greater than 1 along the x-axis? Right, I'm going to start as well here. So the top function is a -3x, and the transition point how about I just put TP? Transition point is x is equal to 1, right? So this is where everything changes right here. Okay, so if we think about this here, are we okay with adding a little 0 at the end here? So for the top function, x is less than or equal to 1, we're still using the -3x. So y-intercept is 0. -3/1 is my slope, so we're going to go down 1, 2, 3 over 1, except I can't use this point any longer because it's not part of my domain anymore for this particular function. So in this case, we have ourselves a open dot there. And we can graph this function now. So going up like this. May not be a very precise straight line there. And then the bottom function is 2x. So again, we're going to add a little 0 in here. So then if I were to use y equals mx plus b, I would start off at 0, except, again, just eyeballing it, not writing anything down. I would go up 2 over 1. So this is where my graph is actually going to start, right here. That's where I can finally put my closed dot, because that's my transition point for the beginning of my new graph here. Right there. So closed dot. Then I'm going to use the slope function again to go up 1, 2 over 1. There it is. There's my next point. And once I have this next point, I'm good. because now I can keep on going here. Again, domain and range. Real quickly here. Yes, question.
Why for 2x plus 0 is it a closed dot instead of open dot?
Question is, why is for 2x plus 0 is it a closed dot instead of an open dot? Because I messed up. That's why. That's absolutely why. Sorry. Good job catching that, Michael. Right here. Notice real quick. Let me go back to this. That's why some of you guys were staring at me funny. Okay, notice this is it right here, right? I was looking at the previous problem here. There it is, right? It goes down. And let me just check. Kenneth, if you correct here. This one, yeah, this one is. All right, this one should have been the closed dot, right? Okay, because we are finishing up at 1, but the last dot belongs to. Yeah, so then this guy should have been the open dot because we're beginning the new graph, but that dot, that beginning dot, does not belong to that graph. Thank you for catching that. Okay, so domain, negative infinity, positive infinity. Kenneth, was that the same stuff that you had an issue with? Or okay. Okay, here, as we're climbing the ladder along the y-axis, I get to -3. And I am including -3 this time. It does touch -3 as the lowest point along this graph. And then from here on out going up, it's forever. So there's my... Okay, good there. Oh, now people are wishing they did read 2.6. Is that what it is? Is that the moaning and the groaning there? Is that what it is? He thought that no one heard him. That's why. Okay. That was graphing piecewise functions. Now let's go the exact opposite way. Let's go backwards on it here. So can we go from a graph back to equation? Ooh, hold on. We talked about it, right? Oh, man. That's no fun. We talked about how we do this. All right. I think we take point slope form. Is that right? Something about point slope form. This is the first problem that we did. Okay, so practice problem number 8. What we have to do is we have to do it for figure B. So it's this one right here. So we're going to have to write the piecewise function. Now notice on figure A, it's disconnected at -2 right here, right? So you know exactly where this graph. So for this particular graph, it's going to be x less than -2. For this one is your domain issue, right? Or less than, sorry, or equal to. What am I messing up here? Okay. Because that function allows the endpoint there. We're good? But these guys, look, they're connected. So this graph, so you're kind of not quite sure. Hold on, who has the connected point? Is the graph going up? I'm sorry, is the graph coming down? Or is the graph that just turned and going up again? So in this case, it doesn't matter because any which way, as long as you get that dot somehow. Does that make sense? And so what you care about is getting that dot in there. Okay, so I'll sort of show it to you both ways here as we do it. Okay, so let's go for it here. Straight lines, that's nice. So I guess I need to figure this out. I need to know the equation of at least that line right there. And then guess what we need to do? We need to figure out the equation of that line going up. Then we need to know the equation of the line going down. All right, so go for it. So -4, 0, and -2, 2. I'm going to start it as well. If you can stay ahead of me, that's cool. If not, let's go with it. So for the graph going down, I have 2 points. -4, 0, -2, -2. I think this is why we practice the slope formula, because given 2 points of a straight line, I can get the slope here. So I'm at -2 minus 0. How about -2 minus a -4? Plus plus. A -2 over 2. And how about a slope of -1 for that first line that we have? So now let's get the equation of the line, because that's what we did for practice problem number 1. So then I plug into this little formula right here. Again, doesn't matter which point I plug in, as long as I plug in any of the point that's actually on the line itself. So I'm going to plug in -4, 0. I'm going to choose that one. So y minus 0. Slope is -1. X subtracting a -4 is really x plus 4. Let's see, distributing the -1 to the x and the 4, and there's my equation. There's my equation of that line going down. So we have to do it 2 more times, right? 2 more times to get us the equation of each of those lines. All right, give you guys like a 20-second head start if you haven't done so already. So I'm looking back at the previous slide here, and I'm seeing -2, -2 as 1 point along that line going up, and then it goes up to 3, 2. So now, getting my slope here, 2 subtract a -2 on top, and about 3 subtract a -2 on the bottom. Well, that's kind of fun, because then that's going to give me plus plus on top. So how about a 4? On the bottom again, plus plus, and a 5, and I get to go into this again. I've written down the equation already, so I'm not going to write it down again. Let me just plug in numbers here. I'm going to plug in 3, 2 this time here, 3, so y minus 2, slope, x minus 3. Question?
On the slope, put 2 plus 2, isn't it? 3. How'd you get that?
Yeah. Question is, how did I get this little guy right here? And I got it by subtracting these guys from each other here. So it's 2 subtract a -2 originally.
Oh, okay.
And then putting in the plus sign, so I'm not subtracting negatives. Okay there now? All right, keep on going with this guy here. Let's see, distributing the 4/5 to the x, that's easy. Distributing the 4/5 to the -3 makes a -12/5, looks like. And in this case, adding, is that right? Adding 2. So let's see real quick here. Let's figure this out real quick. 2 is the same thing as what over 5? So this really would be adding 10 over 5 if you think about it. And then how about 4/5 x minus 2/5? Thank you for doing that quick for me. All right, and last one here. When the graph turns now again, it starts going down. So 3, 2, 4, 0 are the 2 points to make that happen. This one's kind of easy. From the graph itself, you can probably get even the slope there. But again, we're just going to go quickly here. 0 minus 2. 4 minus 3. And how about a -2 over 1, or just -2? Plugging into the slope formula. Slope given, x coordinate given, and voila. How about -2x plus 8? Oof, okay. Let's see what I have here. I have I have this, I have this, and I have this. So now let's write it as a piecewise function. Right, so which way do we go? Especially those corners. Again, those corners, because they're connected, it doesn't matter which way you put those domain restrictions. All right, so let me go. Let's write it one way, and then we'll show you a different way, and both are correct here. So first, our top equation that we've made is a negative x minus 4. And let's see, how am I going to do this here? Again, it does not matter which way you write the domain restrictions because they're all connected here. So I'm going to say this. I'm going to say my end lines are the stuff with the endpoints, and the middle line in the middle is the stuff sort of in between. Good. So I'm going to say this. Let's say x is less than or equal negative 2. So I'm using the top, the function going down. The middle section is the stuff in between everything. And then the last equation holds. And this would be totally cool. We're good? That would be a one correct answer. So kind of careful in the back of the book, because they're just going to give you one answer. Okay? You could have written it like this, and this will be fine too. And again, it's because all the lines are connected to each other. We're good. So let me show another one. I could have written it like this. Now, if I do it like this, I better put a less than or equal to symbol here. Right? One of them has to be equal to the x. This way. Okay, are we good there? Does that make sense? At 3, one of them is going to be less than 3, one's going to be greater than or equal to 3. If I made the middle section to be x less than or equal to 3, then that bottom one would have been x greater than 3. Okay, hopefully that kind of makes sense there. So if the graphs are not connected, very careful how you do the domain restrictions. We're good? If the graphs are connected, doesn't matter which one's the one that connects it. All right, let's keep on going. So this piecewise function really wasn't a new function, right? It was more like just putting different functions together. What? Gotta do it over? No, I don't want to do it over. All right, let me just redraw this here, and hopefully it's not going to draw it again for me. Okay, so here it is. I picked this little point right here, arbitrarily named it 0.6. So my question to you is, what is the biggest integer up to but not going over 0.6? Hold on. Integer. What's the greatest integer? I go with 0. Is that right? Okay. What is the greatest integer without going over 1.2? There it is. You got it. Greatest integer without going over 0.999. Ha! Couldn't catch you. Okay. And the fun part begins. Ready? The greatest integer without going over negative 4.2. Love it. Got some of you guys. Gotta make a little table because I think the visual is a lot better. So if you start counting to negative 4.2, it's gonna be right about there. Is that right? But then again, the greatest integer up to negative 4.2 without going over is negative 5. All right. And this one should be easy one here. So the function value is negative 3.4. So plug it into the function itself would be double bracket it's all yours here. What is f of negative 3.4? Negative 4, I go with it. Yep, cool. Again, if you need a little visual here, there's 1, negative 2, negative 3, negative 4. So negative 3.4 is right here. But negative 4 is the highest integer without going over. What else I was going to mention here? I don't know. Positive 4.7. All right. Greatest integer up to 4.7, but not going over. Yeah, it's going to be a 4. Perfect. Okay, so then the question is, Mr. H, I know that's the lowest one. Is there a function that gives you a integer that's one higher than the lowest one? Right, so you have a ceiling cap on it instead of a low cap on it. So yeah, there is one like that too.
How is that 4 again?
Sure, because if you go 1, 2, 3, 4, 5, 4.7 is right here. So it did not quite reach 5 yet, so therefore the biggest integer up to 4.7 without going over, it's going to be a 4. Almost as it slides down almost to that next bottom there.
So just the way you solve these problems. That's it.
Yeah, there's just going to be numerical ones here. I'm not sure if you graph one or not. I'm not sure. But only 2 people would know because only 2 people read through 2.6. Okay, so here we go. Just a quick view here of something called the library of functions, or library of basic functions here. I have a friend that teaches at Fresno State. He teaches the calc class there. And this is his first day of class right here. First day, section 1.1 of calc is review all library functions. Because we're going to see them, you're going to use them. And so the next day you come in, you take a test on the library of functions. And so you have to know the function, have to graph it, and have to give me your domain and range of it. That's kind of so you've seen these before. Just going to quickly just go through them here. It's something you will refer probably back to it. And anybody know what page number is this on? 234. It's a whole page, yep, of them here, and it gives you the graph of it, domain, range, and again, and remember that increasing, decreasing, or constant? It gives you that information for it, and then any symmetry. Oh wow, all the stuff we've covered so far, kind of fun. Okay, since you guys see it, if you do have a page 234 in front of you. All right, let's go for it here. So constant function, again, domain, notice, is from negative infinity to positive infinity, everything plugged in. And the range is a single value called C. So whenever you get single values only, what you do is you don't put parentheses around it because those means intervals. What you do here is you put set notation around. So you're saying just this particular number, just this set. And that set is just that number. Okay, identity function, we saw that one already. X squared is called a squaring function. And again, I'll let you guys ponder these and look at these here later on. Where is this stuff sort of used at? piecewise functions, right? Let's say you have a identity function coming to 0, 0, then after that it turns into a square function. Well, you can just lay these, in a sense, almost like on top of each other. Use the identity function up to a certain point, use the square function for the rest. So that's why. All right, cubing function, again, things you've seen before. Hopefully this is just like, oh yeah, I remember this one. Oh yeah, I remember this one. So domain and range is the same, it just goes everywhere. Absolute value function, it does have a corner. Domain is everything, the range is 0 and anything up from 0. All right, square root function. We actually graphed that one today, is that right? This one starts off at 0, 0. So that curves and goes upper left there. Cube function, saw the graph of that as well. All right, and two functions we'll see later on, the reciprocal function. This is when you have a fraction and you have a variable inside the bottom of that fraction. You did a lot of stuff with algebra with it. Now we're going to look at more of the graphing aspect to it. So there it is. Notice you have a union now. So you got this little piece right here. So for your domain, everything works except for this one little piece right here. Because if I say, what's the value of 1 over 0? And you're going to say, Mr. H can't do that. And so works up to 0, but not including it, hence the parentheses. Union means there's a break in my graph. And then not a bracket, it's a parenthesis. So anything up to 0, not including. Anything past 0, not including the 0. All right, and then if you take x squared, what happens is that now these arrows go in the same direction now at that point where it cuts off. The reason for it, because if you square a negative, it becomes positive, is that right? Square a positive, still remains positive. This little part right here is the problem. It should be like this as well, right? And it has to close off that infinity symbol or else we're in trouble there. So it should be a parenthesis right here. So domain. All right, that's why we're talking about even and odd right here, because if you have an even number there, it does not include the negatives. Next one over. If it's a 2/3 power, then it can go both ways. Negative or positive, doesn't matter. So therefore the domain is not restricted. And the one that we just saw, the greatest integer function, there it is. So notice domain is everything, because everything will have a value, but your range is individual numbers there, and you put a little dot dot dot, means it keeps on going, and you just start listing integers, so therefore you know the integers keep on going.
Will we get the answer wrong if we don't put the dot dot dot?
Yes, because if you don't put dot dot dot, which means that integer stops, and you have to put the dot 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 both ways as well. It keeps on going both ways.